All right, so let's take a look. I assume that these are X'd out because you don't need to know them, so email me if that changes, if you do need me to go over those. I see some derivatives, I see definition derivative. Okay. Number 4, so an object thrown directly upward is at a height f equals negative 16t squared plus 48t plus 64 feet after t seconds have passed. So what is the initial velocity? So consider this our position. So velocity, VFT, is the derivative of position, which will be negative 32t plus 48. And we want initial velocity, so that's going to be when t equals 0. So when t equals 0, we get 48, and this is feet per second. When does it reach its maximum height? So imagine if an object goes up, it's going to reach a maximum height, and then it's going to go back down. So this is right when the velocity is equal to 0. So remember from above, when we found velocity, we said that was negative 32t plus 48. So we're going to set that equal to 0. So we have 32t equals 48, and we get v equals 1.5. So at 1.5 seconds. Part C says, what is its maximum height? So now we have to go back to the position basically. So what is the maximum height? That's going to be s of 1.5, because at 1.5 that's where it reaches the maximum height. So we have negative 16 times 1.5 squared plus 48 times 1.5 plus 64. So I'm going to plug this in my calculator just to save some time. Double check, but it looks like we should get 100 feet. So when does it hit the ground? Well, imagine, looking back at part B, this is your position. So we know the position, when S of t is equal to 0, it's going to be starting off, and it's also going to be landing. So we're going to take our position function. Oops. Oh, I made it too big by accident. Okay, so let's go back. So our position function was negative 16t squared plus 48t plus 64, and we want to set this equal to 0. Okay, so first thing I'm going to do is I'm going to factor out of 16. So I get t squared minus 3t minus 4. So divide both sides by negative 16, and then we factor. So we get minus 4 and plus 1. So t equals 4, and t equals negative 1. Well, time can't be negative. So at t equals 4 seconds. With what speed does it hit the ground? So at 4 seconds, it's going to hit the ground. So speed, we want to plug into velocity. Speed is just the absolute value, so v of 4. Let's see, so negative 32 times 4 plus 48. You get negative 80. And again, if it said velocity, we would say negative 80 feet per second, but speed is always considered positive, so it's 80 feet per second. Okay, here we have a function, x plus 4 over x squared. give the vertical asymptote x equals c, as well as the associated limits approaching c from the left and c from the right. Well, first thing what I would do is I would take our function and I would find the common denominator, which means I'm going to multiply by x squared on the top and the bottom. So I get f of x is equal to x to the third plus 4 all over x squared. Now, when considering our vertical asymptote, so we basically, now that we have it in this rational function, we look to see if we can simplify anything. We can't, so we set the denominator equal to 0. So there is a vertical asymptote at x equals 0. So we want to look at the limit as x approaches 0 from the left, and we want to look at the limit as x approaches 0 from the right of f of x. Now, there are a number of different ways that we could evaluate this. We could consider graphing this and seeing it's basically going to be positive or negative infinity. So from the left, again, you could also look at plugging in like really small values of, if I plugged in, let's say, -1, I'd still get something positive. And what happens when this gets smaller and smaller? We're going to get, let's confirm that. Let me just take out the graphing calculator. So if I were to graph this, x to the third plus 4 divided by x squared. So that does appear from the left and from the right. We are going to get positive infinity. Determine the critical point of f. Okay, so we could use either the original function or the one that I rewrote. I'll use the original function where we had it written, but I'm going to rewrite the second term as 4x to the -2. So the critical points are where the derivative is equal to 0 or undefined. So we get 1 minus 8x to the -3, or minus 8 over x cubed. So I can see that it's going to be undefined at 0. However, 0 is not in the domain, right? If we think back to the beginning, we can't have 0. So we have to make sure that they also are in the domain. Now we want to consider where it's equal to 0. So x cubed over 8. So x equals 2. So x equals 2 is the critical point. Determine the intervals where f is increasing and decreasing. So what I like to do is I make a number line, and I'm going to call that f prime. Now, remember, we have one critical point, so that's at 2, but I just want to keep in mind at 0, there's an open circle, because that's where the function is undefined. Now I can pick basically I want to pick something to the left of 2 and to the right of 2. Let's say I choose 1. Now remember, I put f prime, so I'm going to test f of 1 into the derivative. So if I plug in f prime of 1, I get 1 minus, and that's going to be minus 8. That would be minus. And to the right of 2, so if I plug in 3, I'm going to have 1 minus 8 over 27. That's going to be positive. So basically it's decreasing, continues to decrease, and then it increases. So it increases in the interval from 2 to infinity, and it decreases from negative infinity, I'm going to put 0, and then from 0 to 2. Now I use brackets around the 2. I don't know how your professor does it, but generally speaking, if it's non-excluded in the domain, we do include the endpoint. But usually most professors, and even on the AP exam as an example, they'll accept parentheses as well. Okay, local maxima or minima. Well, keep in mind that went from negative infinity to infinity. So the reason I like to do this little number line is then I can just kind of see, basically because it goes down and then it goes up, there's a minimum here. And there is no maximum because it goes to infinity, and the end behavior both goes to positive infinity. So my min is going to be f of 2. Now I have to go back to the original to find the actual value. So it's going to be 2 plus 4 over x squared. So 4 over 2 squared. So that becomes 3. So f of 2 equals 3 is the min. Next we want to consider the concavity. Okay, concavity has to do with the second derivative. So I'm going to take the first derivative, which was 1 minus, and I'm going to rewrite this as minus 8x to the negative 3. So when I do my second derivative, that becomes a 0, and I get 24x to the negative 4, or 24 over x to the 4. Now, normally I would set the derivative equal to 0, but that's not going to work. In fact, there's only one place where this is undefined, and that's at x equals 0. And we know that that's not in the domain. So I'm going to make a similar number line. This is with the second derivative. I'm going to put in a 0 and just keep in mind that's an open circle. So if I choose something to the left or to the right of 0 and I test this in my second derivative, no matter what, I'm going to get positive. So it stays concave up, or the domain of the function. So it's concave up from negative infinity to 0, and then from 0 to infinity. Okay, now sketching the graph showing your results for the earlier parts of this problem. I'm guessing they're talking about what do we have here? Well, we have vertical asymptote at 0, and we know there's a minimum at 2, and that minimum was 2 comma 3. So it hits a minimum here. And what else do we have? So it looks, we know it comes going to approach positive infinity here, and here it's going to come down, and it's concave up. I can see that from our results here. This actually, if we look back here, has an oblique asymptote at y equals x. So that's also another, you kind of see it follows that based on that information. Okay, number 6. Find the equation of the line tangent to the curve sine squared x plus cosine y equals xy squared at point 0 pi over 2. Okay, so what does that mean? Well, we want to find our derivative, and then we want to actually plug in 0 for x and pi over 2 for y. So let me see what we have here. So 2 sine x cosine x, that looks good, minus sine of y times y prime, that's fine. And over here we have y squared, and then I have 2xy y prime. You got the y primes on the same side, that's fine. And then we factored out. Okay, so basically I want to evaluate dy dx at the point 0 pi over 2. So I have 2 cosine of 0, sine of 0, minus pi over 2 squared, all over 2 times 0 times pi over 2, plus sine of pi over 2. Well, this was all 0. this is all 0. So I have negative pi squared over 4. And sine of pi over 2 is 1. So that's it. Negative pi squared over 4. Oh, I'm sorry. The equation of the line tangent. So this is actually just our slope. So now the equation of line tangent. So your tangent line, what do we need to find the equation of a line? We need the slope. Remember, dy dx is slope. And we need a point, which we have. So it's going to be y minus pi over 2 equals negative pi squared over 4 times x minus 0, or just times x. So y equals negative pi squared over 4 x plus pi over 2. Okay, number 7. A physics professor decides to curve his exam as follows. If a student receives a score of x on the exam, then curve the score is 10 root x. Then the curved score is 10 root x. Assuming that the range of possible scores in the closed interval from 0 to 100, find the score x that maximizes the benefit of this grade. Okay, so let y equal the difference between the curved score and the initial score. Alright, so you let y equal 10 root x minus x. So let's see. We're finding x that maximizes. Then you find the derivative. The derivative looks fine. So what we did back here, just a reminder, when we find maxima or minima, we want to find the derivative, set it equal to 0, and evaluate. So let's see what we get here. So it's going to be 5 over root x minus 1. So if I add 1, so root x equals 5, so x equals 25. So it looks like 25, and so a score of 25 would maximize it. You can double check. Now remember, these have endpoints, so it goes from 0 to 100. And if I check 25, and this is my dy dx and my y prime, so I check a value here. Yeah, so it is going to give us something positive and then negative. So it goes up and then goes back down. So we can see at x equals 25, that is going to maximize the score. Okay, evaluate the following integrals. Oh, I see. So you need to recognize, I'm guessing your teacher has you recognize there are two. Remember, if y equals tangent of x, then y prime is 1 over 1 plus x squared. Usually most teachers would also like you to know, oh, I'm sorry, that's an inverse. Sine inverse of x, then y prime is 1 over the square root of 1 minus x squared. So it's just a matter of recognizing 1 over 1 plus x squared is the, when we take the antiderivative of that, we get tangent inverse. And then don't forget, if it's an indefinite integral, you should have a plus c at the end here. Okay. Yeah, and the reason we know it's a tangent inverse and not a u substitution is we don't have an x in the numerator. Okay, we would need that in order to use that u substitution. Okay, next one. Looks like you used, I think you're okay with that one. That's good. I see you as circled. Okay, so there's two ways to do this. We could rewrite this as a piecewise function, or you could actually graph the absolute value of 2 minus x. So this is, if you remember what an absolute value function looks like, this is going to look like this. And remember, the integral represents the area under the curve. So if I went from 0 to 5, I'm looking at these two triangular regions. So I have 1/2 base times height for this one, plus 1/2. And the next one is 3 times 3. So I get, so I basically have what, 2 plus 9/2? So 6.5. The other way we would have to do it is to break this function up into two separate integrals. So this is the line negative x plus 2 when x is less than 2, and then it's the line x minus 2 when x is greater than or equal to 2. So then you would just break it up into the integral of from 0 to 2, you would use this part, and then from 2 to 5, you would use this graph. So that's another way to evaluate that. Okay, that's number 9 in the graph. To the right, area of region A is 1, area of region B is 1.8, and the area of region C is 2.7. Give the value. So let's see, negative 1 to 2. So yeah, anything below the curve is going to be negative. So it's going to be negative 1 plus 1.8 minus 2.7, negative 1.9. Yes, that's right. The absolute value, so that's going to make all the areas positive. So that would be kind of like if these all became here. So that should be 1 plus 1.8 plus 2.7. So actually this one should be 5.5. And then from 2 to 1, so when the bounds are switched right, you do want to change that. And then from 1 to 2 is negative 2.7, so you made it positive. That looks good. Okay, a person is using a straw to drink from a conical paper cup whose axis is vertical at a rate of 4 cubic centimeters a second. Okay, so that means so whenever I see a rate and I see cubic something, I know that's a change in the volume. So that's dV dt, and they're basically drinking from a straw, so it's going to be a negative. The volume is decreasing, negative 4 centimeters, cubic centimeters per second. The height of the cup is 10, and the radius, okay, so here this is 10, and the radius at the top is 3. Express the volume of a liquid as a function of its height. So in other words, okay, the problem that we have here is we have too many variables. We have the radius and we have the height, and we only want to have the height. So what ends up happening in a situation like this is when you think about the liquid, okay, the radius is going to change in proportion to the height. So we think about, okay, the radius to the height is 3 to 10. So I want to use this proportion to somehow remove the r here. Okay, well, in that case, I want to solve for r. So I have 10r equals 3h, or r is 3h over 10. So if I take volume, which they give us, which is very generous, 1/3 pi r squared, so I'm going to replace r with 3h over 10 squared times h. Well, let's multiply that out. 1/3 pi, I have 9h squared over 100 times h. So now, let's see, that's going to go in 3 times. So I have 3 pi over 100 h cubed. So now my volume is a function of the height. How fast is the height of the liquid changing when the height of the liquid is 5 centimeters? Okay, so let's use this. So d of h equals 3 pi 100 h cubed. So I want to find dv dt, so that's fine. So I want to find d dt of this. Nice thing is now we just have it in terms of the height. of dv dt. So I have 3 pi 100 times 3h squared dh dt. So just keep in mind this is kind of like implicit differentiation, so whenever I get to the h cubed, I have to multiply by dh dt. Now that's actually what I'm trying to find. So I'm going to plug in, it said what, the height is 5, and I know dv dt. I'm going to put -4, because remember that was a negative rate. So I have 9 pi over 100 times 5 squared dh dt. So I have, let's see, 9 times 25 divided by 100. So I have, another room here, 9 pi over 4 dh dt equals -4. So I'm going to multiply both sides by 4 over 9 pi. 4 over 9 pi. So dh dt is -16 over 9 pi, whatever that is, centimeters per second. Okay, and keep in mind, if you're drinking from the straw, right, the height is decreasing, so it makes sense that it came out to be negative. Okay. Let's see. We circle these. Problem 3 for the function y equals f of x, whose graph is given below. What interval corresponds to f double prime is positive, so this is where it's concave up. So where does it appear to be concave up? I'm going to say from x3 to x5. Right, so we want to think of like right in the middle of where it's concave down and switches to concave up. I'm going to try to highlight. So that's what it looks like to me. It looks like this is where it's concave down, where I traced in red, and then concave up, where I traced in blue. So where is f prime negative? I'm going to say from, well, I don't know if we want to include negative infinity or -1. Yeah, I mean, I guess I'd probably say it's concave down from negative infinity to x3, and then x5 to infinity. Where is f prime increasing? Okay, so that's actually a clever question, because where is f prime increasing? F prime is increasing when f prime is positive, which we already answered. It's actually the same answer as part B, x3 to x5. Where is f prime decreasing? It's actually the same thing as C. That's when f double prime is negative. So it's the same answer as C. Okay. Is that all you circled? Okay. Well, take a look at this. Let me know. I'll be around mostly tomorrow, so email me if you have more questions. Okay.